So Jonathan said he wanted a short introduction. It's already been long, so I'll keep this very brief. Jonathan got his PhD at Princeton with Simon. This seems to be a theme around here. Wait a second. Fred did. Wait, I did. And the one thing that's, and you can read other facts on his baseball card, like he's now at McMaster. And the one thing that's not on there is he did a postdoc in Taiwan, and he's fluent in Chinese. So by a show of hands, how many would like the lecture in English? And how many would like it in Chinese? So, Jonathan, it's going to be a pleasure.
Am I on? Oh, thank you. I forgot my water. That's good. So, I'm Jonathan. And as Alan said, I'm teaching at McMaster. I'm also teaching with the ICI3D. We do, among other things, annual workshops in Cape Town on mathematical modeling of epidemiological data. And I think it's something that many people here might be interested in. I'm going to give a fairly data-free talk, and almost completely statistics-free talk, but I've talked to many people here about engaging more with data and engaging more statistically with data. And if you're interested in another great workshop in another great venue, you can check out the ICI3D. Everything in this talk, all the code I used to do all the pictures and all the code I used to make the talk is, in theory, already available on GitHub. So those are my 3 URLs. It's really an honor to be invited. Thank you to the organizers. I am feeling a little bit annoyed at the other plenary speakers who have set, in my opinion, entirely too high a standard for plenary talks. But maybe, you know, Thursday morning it's okay to let the standard go a little bit. I have no idea what that's there for. So I'm going to talk to you about measuring epidemic spread through populations. So I'm going to be focusing on individuals as my units and how epidemics spread through populations. And I'm going to talk about the 2 most common ways we measure them, how these are linked, and maybe question a sort of religion around the idea of R0, the basic reproductive number, which I'm usually going to refer to here as big R. So infectious diseases are a big deal. These are people being afraid of the Mexican flu, which turned out not to be as big a deal as people thought, which does not mean that they were wrong to be afraid of it. And these are people being afraid of Ebola. This is an Ebola safe burial response team. And models of infectious disease have become a big deal. People, when there's infectious disease outbreaks, people consult modelers from the beginning. Modelers were very influential in talking about the response to Ebola particularly. They're deeply involved now in the response to HIV. And models are the tool we use to link between assumptions and outcomes. The spread of an infectious disease is essentially a dynamical process. And dynamical models are the only thing that allows us to get from here, which is an Ebola ward where they're practicing more or less best practices in terms of infection control, to here, which is a time course of the Ebola outbreak in Liberia. And models help us go in both directions. Models not only allow us to ask, if we do something here, what might be the effect be at the population level? Models are also the tool we use to look at population level data and try to infer what might be happening on the ground. And that's all I'll say about that. And I'll talk one more time about the fact that this is a stats-free talk. Mostly, I've been moving more and more towards stats. I believe that we need dynamical models to bridge scales, but in a messy world, we need statistical frameworks to interpret the data that we have. And we need tools that can incorporate dynamical mechanisms into frameworks that allow statistical inference. I also believe, though, in a complicated world, in simple dynamical models and in intuition and in simple dynamical theories that may help us navigate the complicated world of these complicated statistical models and complicated statistical fits. So what are my two key parameters? The first is speed, which I'm going to call little r. And little r is the measure of the instantaneous rate of change of disease. Given how much disease you have, how well is it spreading itself? It has units of 1 over time. And many of you will not be surprised that the initial rate of spread is exponential. The disease is going to spread exponentially like e to the RT. And I'm also, you're all mathematicians, so I feel I can do this without fear, unlike in many audiences. I'm also going to refer to the characteristic time scale of spread as capital C, and that's just 1 over little r, and it has units of time. So here's an example of data. These are cumulative incidence counts from the Ebola epidemic, and a case where it looks like we have exponential growth. So when you see this data at the beginning of the Ebola epidemic, the first thing you want to do is estimate little r, because you can tell what it is. And then you start asking, what can little r tell me about how Ebola might spread? Here's an example. And the characteristic time scale here, we estimate it to be about 1 month at the beginning, which is fast, but not super fast. When the Mexican flu came out, people estimated the characteristic time scale at 1 week, which they also said was fast, but not super fast, which seems odd, because it's 4 times faster, so one of them should be fast, or else one of them should be slow. And I was particularly struck at the beginning of the HIV epidemic when first measured the rate of increase in sub-Saharan Africa. The characteristic time there was 18 months, which people agreed was horrifyingly fast, even though some of you might feel like that's slower, say, than 1 month. And we'll come back to that via the root of our other key parameter, which is capital R. So we describe epidemic strength using capital R. Many of you know it as R0. And R0 is sort of like the conventional, is the movie star of the story. And R0 is, in fact, a movie star. R0 has appeared in many of the movies that talk about outbreaks. Doesn't usually get top billings, never won any Academy Awards. Big R is the number of potential new cases per case. So if I walked into this room, to this conference with a brand new disease, and I was sick during the conference, we would want to ask, on average, how many people would I expect to infect? That's big R, and big R typically doesn't account for the proportion susceptible. We can give it a subscript if we wanted to. But to eliminate disease, we must reduce effective reproduction by a factor of big R. And big R also tells us something about equilibrium, because one way to reduce disease transmission, the number of cases per case, is to reduce the number of susceptibles. So on average, from simple models, we might expect to find a proportion of the population 1 over R that's susceptible at equilibrium, or the inverse of that as the proportion affected by the disease. And this paradigm was really founded by Ronald Ross, who is amazingly the person who showed mosquitoes transmit malaria, and also really the founder of this classical way of thinking about diseases from a mathematical point of view. He argued that probably yellow fever in Panama had an R0 of about 2. So he argued that mosquito control programs in Panama pre-canal would be worth doing, would be far more effective than people expected, because he said if you can reduce the number of mosquitoes by a factor of 3 or 4, you might expect to reduce the force of transmission of yellow fever by a factor of 3 or 4. But in fact, what he predicted is there would be less than 1 case per case, and the incidence would just keep going down and down and down. And that was sort of correct. They did the control, and it worked better than they expected, but not as well as he expected. And the reason for that, and that's a big theme that I'm going to try not to get tangled up in, is population heterogeneity. So if you want to know more about this particular weakness in R0, you should attend Jerlan and John's session on heterogeneity yesterday. It was a good session. So we often know little r, and we often want to know big R. And what links between them is the generation interval. So the generation interval is the amount of time it takes from when I get infected to the time when I infect you. So here's a sample. These are in days, which I said. This is an estimate of the generation interval distribution from the West African Ebola epidemic. So most people infect each other between 10 or 20 days after they themselves became infected. And we can ask, if we know little r and we know the generation interval, do fast disease generations mean more danger or less danger? As mathematical modelers, we might have one perspective, and people on the ground, statisticians, might have another perspective. So if Ebola generations are faster than I think, is that good or bad? And that fundamentally depends on what else I know. As modelers, we start from parameters. The parameters often point us to big R. If I know big R, right, if I know that I'm going to infect 3 people, then the faster I infect them, the worse. So faster generations might mean more danger and a faster growth rate. Conversely, however, and in fact this goes hand in hand, if I know little r, faster generations have the opposite effect. If I know little r, which was the case with the Ebola epidemic, the faster the generations are, the less I need to transmit in each generation to observe what I've observed. So I have a picture of that. If I imagine this curve, this increasing exponential curve is fixed, if I think the generations are relatively slow, then I'm going to be taking relatively big steps up. And if I think the generations are fast, I'm going to be taking relatively small steps up. And that's, of course, the answer to why 2 weeks and 1 week don't seem that fast, because they don't seem that fast compared to the generation interval. Flu has extremely fast generation intervals. So when it was spreading with a characteristic time of 1 week, that's a little bit of a relief. Whereas HIV has very long generation intervals. So when people estimated the characteristic time of spread at 18 months, they were comparing that to a generation time of 4 years and saying, boy, it looks like HIV has a very high R0, and making really frightening projections. Right around here is when the super frightening projections came out. Some of you will remember them. So I like to think of epidemic speed as a product. This is how the danger thing makes sense to me. Epidemic speed, as a dynamicist, emerges from the generation speed and the epidemic strength. And in this context, it makes sense that if what we know is the speed, if what we know is little r, then generation speed is going to have a different kind of effect on our conclusions. Unfortunately, this simple product analogy is wrong, and I'm going to talk about ways in which we can make it closer. But for now, I'm just going to say epidemic speed is a product of something to do with generation speed and something to do with epidemic strength. Okay, so how are we going to link little r and big R? Well, we need to make a model, and a lot of us are familiar with this kind of model. Raise your hand if you're familiar with this kind of model. Okay, so maybe I'll talk about it less. This model, I'll say what it is. These people are susceptible. They can be affected by the infected people, and then they become infected. They eventually become recovered. These people wait a while before they start infecting other people. And this, there's something wrong with my mouse, and this framework naturally suggests ordinary differential equations. It also naturally suggests Markov processes, and it's been very rich. It's not the framework I'm going to use. I'm going to use a slightly broader framework, which is the Renewal Equation, where we imagine instead of counting the number of people infected, we count the number of new cases at any given time. So that's little I of t. And that's very often what's reported to health authorities and eventually to modelers. So little I is the rate of new infections. And what I'm going to say, my key thing here is a kernel, which I'm going to occasionally factor into other pieces. I'm going to say that the kernel is how infectious I am at any given time after I myself got infected on average. And so I integrate out to infinity how infectious I am at any given time. And then I multiply that by the proportion of the population susceptible. I guess I should have had those words up there while I was saying them. And very often, and for most of the rest of this talk, I'm going to think about S as constant, and you can either treat it as 1 or you can imagine rescaling the equation, but I'm going to leave that alone. And now this becomes a linear equation, because unlike S, K is not necessarily changing as part of my dynamical system. This becomes a linear equation to which I expect to find a simple exponential solution. So here's my picture of the infection kernel. So K is how infectious. This is highly idealized, or sorry, too smooth, but based on real Ebola data. So this is how infectious I might be at various times after being infected, and I'm going to factor that. The area under this curve is unitless and is in fact big R, and if I divide by big R, I get the generation interval distribution, which is something I might be trying to measure from data. So again, my words from my mouth have run ahead of my words on the slide, but this is what we do. We imagine we can measure or estimate something about the kernel and break it into a generation distribution and big R, or we might do it the other way. We might estimate big R and the distribution and try to reconstruct the kernel. What is the link now that we have the renewal distribution? And this is the key equation of my talk. I did not invent it independently of Euler or Lacka. Or maybe I did, but it's too long ago to remember. If we neglect changes in S, we expect exponential growth, and we can very simply solve implicitly for the rate R. That the total of the discounted contributions from the kernel is 1. That value of R, which has to be unique, is our solution. And we can write this in terms of, we can factor K into R and G and move the R over here. So 1 over capital R. This is now our equation that uses the generation distribution to link little r and big R. And this is very often thanks to a very nice paper. I have a sort of love-hate relationship with this paper by Wallinga and Lipsitch. They really took this Euler-Locke idea and moved it over to epidemiology and made it into something that people use, but they chose to talk about it as generating functions, and for that reason, or perhaps for some other reason, it's become very much a black box. In the field, people are working with disease data, they measure things, and they run it through this weird generating function thing. Why is it a generating function? And get the answer. And there's a lot of useful things here, but I'm going to talk about maybe more intuitive ways of thinking about the same link. So if you define an effective generation time so that it follows the equation that you want it to follow, ecologists here will be familiar with this equation, where capital R, the reproductive number, is e to the growth rate times the generation length. That doesn't work easily in this equation, so I'm just going to insist that it work and ask them what my effective generation time is, and I get something really nice. Okay, just take my equation, I'm going to rewrite it in terms of expectations and in terms of my definition, and what I find is that G hat is kind of a filtered mean. It's a representative value. G hat is the, these are meant to be equivalent. I'm writing this integral in a way that's more intuitive to me, but not necessarily to you, as an expectation. So the integral is the because G is a distribution, the integral is an expected value of this discount factor over my generation distribution. And I'm going to say G hat then is the representative value that gives you the same answer as if you take that average. So filtered means, again, this is what I just said, but I feel like I should give you a chance to look at the words. Filtered means is a generalization of a lot of things that we know about. So the geometric mean you can think of as a filtered mean if you use the log function, the harmonic mean if you use the reciprocal function, the root mean square if you use the square function. It just occurs to me I should have added the arithmetic mean, right, which is what you would get if you use the identity function. And now we can write the linking framework with an equation. The epidemic speed is the product of something about generation speed and something about epidemic strength. And particularly, it's the generation speed measured using the effective mean generation time times the log of big R. And here are some pictures which I may go through quickly in the interest of time, but basically you have a distribution. It has a mean. I'm going to call this G bar. Or you can apply the filtering function, take the mean over here, and then you get somebody who can't use their mouse, and then you get a different mean. And this is, in fact, the correct value that we would use to link little r and big R. As little r changes, the filtered mean gets closer to the true mean. And it's important to note the filtered mean sometimes feels like a weighted mean, but it's actually pretty different and a little bit deeper than a weighted mean. And in particular, I've made C a little bit longer than my mean generation time, and I see that I have a very small deviation here, whereas if this were a weighted mean, I would still have a big skew to the left. So filtered means have intuitive properties, and we actually used them in thinking about the Ebola outbreak. Shifts in distribution shift the mean about how you would expect. More late transmission is always going to increase G hat, which in turn is going to mean a higher capital R, if we know little r. And as the distribution gets narrower, since it's a mean, as the distribution gets narrower, we get more and more certainty that G hat is going to look like the values, like the middle value of our distribution. The filtering function is just the function associated with the discount, the exponential growth of the epidemic. So we applied this when we were thinking about the question of how much Ebola transmission occurred before versus after death. I don't know how many of you are familiar with this story, but one of the things that went on in the West African Ebola epidemic was funeral transmission. Big, elaborate funeral rituals that involved people handling the body and getting Ebola. And the question is how much transmission happens after death and how that is going to affect our estimates of what's going on. And so we made a box model that might be familiar to some of you. And these are very standard things where you first add deaths, and then we just added a little blue arrow saying, well, dead people can also transmit Ebola, which is true. And we asked, can you tell the difference from these data? No. Different values of R0 corresponding to different values of post-burial transmission give very different estimates of R0 and very different long-term estimates of what's going on with the Ebola epidemic, none of which had much to do with what actually happened to the Ebola epidemic, fortunately. But different parameters produce indistinguishable early dynamics, but more after death transmission always implies a higher R0. You don't need a black box or a big statistical fit. As you move transmission later, you're increasing G hat, you're increasing your estimate of little r. These other things seem trivial to me. So that's one way I've thought about linking little r and big R. And to me, it's very intuitive, but not always practical. The filtered mean is useful but complicated. It has a lot of the features you want from a mean, but not all of them. And in particular, it's not scale-free. It depends on the scale that's set by the characteristic time G. So unless the generation interval is absolutely fixed, then G hat is going to increase even if G doesn't change. We could also ask the question, I've given you this equation, capital R equals E to this product, but some of you will be familiar with the simple ODE result that capital R is equal to 1 plus a very similar looking product. So how do those two go together? And what we've done is we made a moment approximation. We connect these two quantities roughly by assuming a gamma distribution, although that's not how we arrived there. You can make a moment approximation. We define a single shape variable, a single unitless shape variable, which is the squared coefficient of variation of the generation distribution. And we now have an approximate framework that depends not on this G hat, this nice intuitive but slightly fuzzy quantity, but on G bar, the actual estimated mean generation time. And we can ask, what does it look like and when is it useful? So what it looks like is the compound interest interpretation of the exponential. And it spans all the way from the linear function that we think we understand to the exponential function that we think we understand, and with everything in between. So this approximation implies that so here I'm giving you distributions with the mean time of Ebola, but with different values of kappa. and these are gamma distributions. The exponential is a special case of the gamma distribution. So with the exponential distribution, kappa equals 1, and we get a straight line relationship between the exponential growth rate per generation and our estimate of capital R. As we make the generation interval narrower, this curve goes up and up until eventually it approaches the exponential. So it spans those two limits. And we can also come up with a qualitative reason why should smaller values of kappa mean this curve is sharper. Well, for a given value of g hat, smaller values of kappa mean less variation in the generation interval, therefore less compounding of growth. There's less people who are going to get sick today, make you sick tomorrow, and then you're going to make David Earn sick the day after tomorrow. Or maybe you won't. And therefore, if there's less compounding of growth, we need a bigger value of capital R to explain what we've seen in little r. So we fit this simple approximation to the data that we saw from Ebola, and what we did is we tried to make a fairly realistic and not very gamma-ish, model of the generation distribution and ask what's the real, for our idealization, what's the real relationship between big R and little r, and what do we get from our simple approximation. And so what you're seeing here, the black lines are the approximations. I drew the straight line and the exponential for reference. The black curve in between is the thing we get from a single moment approximation. The blue curve is the thing we get from our realistic, detailed thing that's not meant to look much like a gamma. And the black points are estimates that use, yet again, a slightly different methodology from the 3 West African outbreak countries. And I'm claiming that this looks pretty good for an approximation that we can understand so quickly. And so we can go back to the linking framework and again write little r as a product. Now we have the thing that we want over here, 1 over g hat, our estimate of the epidemic speed. But now we need this slightly complicated, I guess we can call it a generalized logarithm to figure out what we mean by something to do with epidemic strength. So we've tried it on other diseases. In the interest of time, I'm going to skip that. I will say that I wanted to try it for measles because measles has a large R naught, and it just works suspiciously well. I'm sure there are reasons for that. I don't think the approximation is as good as measles think it does. I don't think the approximation is as good as measles think it is. It doesn't work that well for rabies. Rabies has very long and highly variable latent periods, and we found that we can improve. It's less elegant, but we can improve it by admitting that this isn't just a moment approximation, but really a gamma-based approximation. And then you can get better approximations. Going back to the Ebola example, this could be a really good framework for estimating and propagating error if you had data from Ebola, but it's less clear than the filtered mean in terms of the intuition, because burial transmission increases mean generation interval, which increases our estimate of R, but it also increases variation. And so inside this framework, it's not completely obvious that more burial transmission would increase our estimate of big R. Whereas if we use the simpler but less quantitatively useful intuition, we can see immediately why more burial transmission must increase our estimate. So in summary, generation intervals are what we use to link, and we could use better methods for estimating them and propagating uncertainty and for understanding the uncertainties that we're propagating. And for many practical applications, you can't get away with just the mean generation interval, but you may get away with the mean and the coefficient of variation. Okay, I'm going to talk very briefly, in the interest of time again, about how we measure generation intervals. You can measure generation intervals by observing patients. How infectious do you look at various different times? Or we can measure generation intervals by observing populations. Who seems to have infected whom, and when did they seem to do it? Or who got sick when, and when did they who infected whom, when did they get sick, and can we sort of backcast when they got sick. And interestingly, if you measure it at the population level, this was noticed first through models, contact tracing intervals can look systematically different at different times. And this is a known problem of why, but we've again tried to put this on a slightly sounder intuitive basis. We define the intrinsic interval, right? That's my kernel. That's how infectious I am. But we could also ask the forward interval. Everybody I infected at this conference, I'm going to treat as a cohort, and I'm going to ask when, I didn't mention that that was a real thing. I'm going to ask, when are you going to infect the second generation? Or we could look at a backward interval. Who's sick now? Who probably infected them? And it might seem, intuitively it seems these should all be the same, but there's a simple reason why they're not. And it's because, well, I'll start with the example and then I'll give the reason. Generation intervals in particular, and this is the most important reason to worry about it, look shorter at the beginning of the epidemic. I wasn't infected 3 weeks ago, not because you're not infectious 3 weeks later, because there was nobody who was infected. Sorry, the person who infected me didn't get infected 3 weeks ago, not because that person wouldn't be able to infect me, but because 3 weeks ago there was almost nobody here with Ebola, right? The clear case is the HIV epidemic. When we first started worrying about it, these people here didn't get infected 5 or 10 years ago. Sorry, didn't get infected by people who were infected 5 or 10 years ago because there was nobody in their population who was infected 5 or 10 years ago. So more people are infectious right now. They haven't finished their transmitting. We're biased in the beginning towards observing faster events. We can make a simple framework. I'm going to rush through these equations, which I was warned not to do with mathematicians. But we have this simple equation. I was infected at time s. I would infect you at time t. What can affect the backward interval is only the kernel plus the number of people who are in IS, the number of people who were infected at time s and are therefore available to infect me, and similarly for the forward interval. And I'm just going to say that this works. You can look at how incidence is changing and predict in a simulation. So these are simulation points and ODE points, and you see that it works very well. And so we understand and correct for these contact tracing intervals. And we also have the idea of the backward generation interval as something that we might be able to observe directly. How long am I supposed to talk for? 45 minutes? Okay. I maybe should have asked that 6 months ago when I was invited. So now I'm going to go back to my measures of strength and speed, and I'm going to try to poke a little bit at the religion of R naught. So R naught is R or R naught, big R for me, is the expected number of new cases per case, and it's the thing we're supposed to want to know. It's the movie star. Little r is very often the thing we see first, right? How fast is the disease spreading? So why is big R better than little r? Well, big R is better for long-term predictions, but if you're actually dealing with these things, you may notice that little r is better for short-term predictions. There's absolutely nothing wrong with making good short-term predictions. Big R, and this one has been niggling at me for 20 years, and I sort of feel this sense of release. Big R gives a threshold for spread, right? I must infect at least one person. It's a threshold. You make this sharp curve. It's all very exciting. But people keep noticing and then suppressing. Little r obviously gives a threshold for spread too, right? Little r is bigger than 0 or less than 0. It's a perfectly good threshold. I don't know why we sort of have a religion around the one and not the other. Finally, in the history of it, and I should have mentioned earlier, and I'll mention now, Ronald Ross I mentioned, and Anderson and Mayer, the other big people, who talked about comparing big R to the intervention strength. Right? Little r tells you what you need to do to get rid of the disease. Right? So Anderson and May used big R roughly to tell us what it would take to get rid of measles, and Ross used big R to tell us roughly what it would take to get rid of yellow fever. And those were both wrong, but also both quite useful. Wrong because of Gerlach and John and the disease heterogeneity. So what about little r? is there a sensible way to think about control in this speed framework? And the way I stumbled onto this was thinking about one of the most exciting things that's going on in the world now, which is that HIV treatment is now really, really good. It's good for the patients, and it's good for other people. If your HIV is well controlled by standard therapy, you're not going to be able to make other people sick, to the point where people debate whether there should even be a condom recommendation for people whose HIV is well controlled. And so we could ask now if treatment of HIV used to be almost a double-edged sword. People didn't want to talk about it for reasons that I should absolutely avoid getting into. But you treat people and they live for longer and maybe spread more. Now it's absolutely not that. You treat people, it's good for the patients, good for the population. And is this it? Are we going to be able to turn the corner on HIV now? So when people started asking that, the first thing they asked is, are HIV generations fast or slow? You have HIV for about 10 years, but you may be highly active either biologically or sociologically for the first few months of that. And there's a lot of debate about how much HIV transmission happens early versus late, and that's going to have a big effect on how quickly you have to find people, get them to be tested, and treat them. So fast generations mean that testing and treatment will help less. And this was like the big debate in the question. And now it's not, because fast generations also mean lower epidemic strength, right? And so if the generations, we know little r, if the generations are fast, then testing and treatment doesn't reach as much of the transmission, but it also doesn't need to. And there was a very good and very involved, intricate, detailed paper by Eaton and Hallett, which showed that predicted effectiveness over a wide range of models is minimally sensitive to the proportion of early transmission, exactly the opposite of what people thought. And that's because if HIV transmission is intrinsically fast, then testing and treatment prevents a low proportion of transmission, but that's fine. And similarly, if it's intrinsically slow, R is very high, but testing and treatment, in theory, can be highly effective. And I started thinking, well, is there another way to think about that? Is there a simpler way to think about it? And what if instead of thinking about reducing transmission by a factor, which is the classic paradigm, what if we think about the idealized case where we're identifying and removing people with HIV at a constant rate, and what would that rate have to be? And the answer is the Euler-Locke equation. You ask yourself that question, and you write down the Euler-Locke equation. You would have to get people out of the kernel at rate r so that it integrates to 1. You want to bring the number of new cases per case down to 1. So what you find in this idealized case is that your required treatment hazard is exactly equal to little r. So not only does little r have a threshold for spread, just like big R, but it's a control threshold, just like big R. And that's what I thought. And so for the rest of the talk, I'm going to develop that framework just a little more rigorously. I'm going to redefine the classic paradigm of intervention strength in a way that's well suited to doing a parallel story about intervention speed. I'm going to give you an example, and I'm going to let you all go, hopefully roughly on time. So the conventional paradigm, here's a kernel for Ebola, right? This is about smooth, because I'm a mathematician and I'm making these curves in a hurry. This is about how infectious we might think people are. And so big R is the area under the curve. And if I was going to effectively vaccinate a proportion of the population, big R tells me what proportion of the population I need to vaccinate. If big R is 4, then I have to reduce the number of susceptibles by a factor of 4. But I could also ask, what if I had a more speed-like intervention? What if I was finding people and trying to put them in quarantine, infection control? Here I don't have a constant intervention strength, but I could still ask, what's the area under the curve? How well have I controlled the spread of disease? And I'm going to do that by defining a strength of intervention as a factor, sort of the reciprocal of the way we usually think about it, because I want to think of it as a strength. So I'm going to divide by it instead of multiply it. So I'm going to say my intervention takes kernel to kernel hat, where the kernel hat is the kernel divided by L. So if I was vaccinating 75% of the population, L of tau would be 4, and I should probably remind you tau with the kernel is the time since somebody was infected. So we can now define intervention strength as the amount by which the intervention reduces transmission, and we can solve for it, and what we get is that it's another nice filtered mean. It's the harmonic mean of strength averaged over the intrinsic generation interval. And we can control the outbreak if theta is bigger than r. And all I've done is come up with a different coding, a slightly different way to talk about the classic paradigm of big R and control. And the reason I've done that is I now want to try to do it with speed. So little r is the epidemic speed, and it's the discount rate that's required to balance the tendency to grow. So if I solve the Euler equation, then I see that little r is the rate at which I have to reduce this in order to get this distribution. B is the backward generation interval. In particular, it's the backward generation interval early in spread. And conversely, I can think of that as my control. How quickly do I need to find people and get them into safe rooms where they're not going to give other people Ebola if I want Ebola to go away? But just like strength, I could also think of a different intervention. What if I had a condom intervention? Does it make sense? Sorry, I suddenly switched from Ebola to HIV. Condom interventions do not make much sense for Ebola. If I had a vaccination intervention, does it make sense to think of that as a speed? And I can try doing the analogous thing. I'm going to define the speed as r minus r hat, and I'm going to see if I get a nice equation for it, and the answer is almost. So here's my equation for phi. It's an expectation, which is fascinating to me, over the backwards generation interval, and it's sort of a mean. And I'm going, in the interest of time, I'm not going to get hung up on that. I'm just going to say it's a mean in the sense that it's a representative value. That if h was constant, if h is constant, if we have a constant rate in our idealized infection, then L is e to the ht, which cancels e to the phi t, and that's the answer. So I'll say that a little more clearly, hopefully, in a second. And the outbreak can be controlled. We can measure intervention speed in a way that kind of makes sense, and we can say the outbreak can be controlled if phi is bigger than r. So to recap, the strength paradigm, we start with our kernel, we factor it in a way that tells us big R and gives us an intrinsic generation interval, and then we calculate the strength of intervention. If the strength is constant, then if L is a constant, then the strength of intervention is just L, and in general, it's a harmonic mean across the intrinsic generation interval. The speed paradigm, and blah. The speed paradigm, we also factor the kernel, but we factor it differently. R is the speed of the epidemic, and B is the backward generation. And we also have a mean. We have a constant hazard of reducing risk as tau increases, then phi is just h. Otherwise, it's a weird mean over the backward generation interval. And again, the epidemic is controlled if phi is bigger than r. So here's the part I said I would say more clearly. If hazard is constant, then the speed of the intervention is the speed of the intervention. That may not have been more clear. So an example, HIV, we think we know the initial speed of epidemic spread. There's a lot of things going on, and other things have changed to make this curve suddenly go down. But we think we know the initial epidemic spread. We don't really think we know the proportion of early transmission. So here is a baseline scenario. And if we ask, so people are high here because they might be particularly socially or biologically active. You have this short viremia, and then they get more infectious for a while, and they start dying or getting sick and having less sex. But to match little r in the baseline scenario, we need a reproductive number of 3. If we increase this early phase, make it more important, then we need a smaller reproductive number to explain the same data. Whereas if we decrease the early proportion, we predict a much higher and scarier reproductive number for HIV. And we can do this for a whole bunch of values and say, for a given assumption about the importance of early transmission, what is our estimate of big R? And we can compare that, and we want to compare that to two different interventions. One is we imagine we somehow get people to have sex more safely. And I use condoms as a shorthand for that. And that's an intervention. We're going to imagine that we come in, we educate people, they change their behavior, it changes. So the strength of that intervention doesn't depend on how long you've been, doesn't depend on whether you know how to use your mouse, doesn't depend on how long you've been infected. It's a constant. Or we have the idea of testing and treating, and I made a fairly complicated hazard. This is meant to be a pseudo-realistic scenario where people are being encouraged to get tested, and if they're tested, you link them to medical care and try to treat them. And so again, we have two different effects on the transmission kernel, and it's how it works out is going to depend on what we think the original transmission kernel looks like. And we can take our condom intervention and we can ask for different values of the early proportion, do we think it's going to work, right? So the answer is the condom intervention has a strength of about 3.5, and it's going to work if the early proportion is high, right? If R0 is low because transmission is happening fast, then the condom intervention is going to work, and not conversely. We can do the same thing for test and treat. Right. I was trying to figure out why I didn't show you graphs of how I calculated this mean, but the answer is because the mean is the constant value. For test and treat, we now have to take a mean of this strength, right? This strength is increasing from 1, I guess, because 1 means we're dividing by 1. Strength is increasing from 1 to almost 70, and we have to take a complicated mean, but we have to take a complicated mean over the intrinsic generation interval, and we find that if early transmission is low, we estimate a high strength, right? Because we're finding people before they do most of their transmitting. And if early transmission is high, we estimate a low strength, and we can make a similar graph. So as the early proportion of transmission decreases, as it decreases, it looks like it should get harder for testing, treating to work, but it's also more effective. Or conversely, as test and treat loses strength, as our estimate of test and treat strength goes down, so goes down our estimate of the epidemic strength. And this is sort of the opposite of what people thought. When we started talking about condoms for HIV, nobody worried about early proportion because we know the strength of the condom intervention, right? If we're getting 80% of people to use condoms, the strength is 5. People worried about the strength of test and treat in context of early transmission because it's changing, but that's exactly wrong. It's the condom that's going to change its answer, and test and treat that's not. And that's one way to think about that more clearly, I hope, if you're not all exhausted by now, is the speed paradigm. So I can do this same exact calculation. Instead of using big R, I'm going to use little r, and the picture, I claim, is clearer. So here is my realistic hazard function. At first, there's no way to know you have AIDS. Then you're sort of hopefully trying to get tested and treated. And then I assume conservatively that the hazard of finding people goes down because the people who are the kind of people you're likely to find who have access to medical care and so on have probably already been found. So this is the same, this is the hazard that corresponds to my same assumption. And what you find is, first of all, it's relatively constant over an important area, but even more importantly, the backward generation interval, which is what we're averaging over, shows much less variation than the forward generation interval. So those two things combined to mean that our estimate of the speed of this intervention is actually fairly robust. Okay? And our estimate of the speed of spread in this cartoon is extremely robust, right? In this cartoon, we know the speed. It's what we started with. Obviously, we can add other kinds of uncertainty to this picture, but really thinking on the speed axis works better in this particular case. That's why test and treat doesn't care about early proportion, because we think we know the speed of spread, and we basically think we know the speed of our test and treat scenario. Whether we can achieve our test and treat scenario is, of course, another question. We can also take the condom intervention and at least formally measure it on the speed scale, even though it's really just a delta function at time 0. So maybe that's a hard thing to have an intuition for. But the point is, it formally works. And strength and speed, so it's important. I've really done, so I showed you the strength framework, I showed you the speed framework, and I got the same answers in terms of what's going to work. And it's because it's really the same calculation. In some deep topological sense, I can transform these into the same calculation. It's really two different ways of looking at the question. And the question is then, which of these ways is useful for a particular application? So for measles, we may have better tools to estimate big R, whereas for the Mexican flu, when we were first worried about it in Mexico, we had better tools to estimate little r. We might also have interventions that we think are pretty strength-like, right? Here's a 2-year-old getting a vaccine, and we think that she's just probably not going to get the infection. And here, this is representing testing and treating. This is Archbishop Desmond Tutu getting an HIV test, either because he had a reason for concern or because he was trying to set a good example, or both. And so measles is a good example where the old paradigm is great. Most of our information is strength-like. The vaccine is also strength-like. I would say the current HIV situation is pretty speed-like, and that provides us a good starting point to assess our uncertainties and what's working and what's not. Ebola vaccination is more complicated. During the outbreak, the information was pretty speed-like. The interventions we could talk for a long time about to the extent which they were speed-like or strength-like, including vaccination, because a lot of the vaccination that might have happened if the epidemic had continued was going to be reactive vaccination, which could turn out to be speed-like, for all I know. So the conclusion is little r, big R have more in common than we think. And you don't have to apologize. If you're estimating little r, you don't have to bow down to the people who say you should be estimating big R. You say, yes, big R is also good. Sometimes the strength perspective is a clearer way to see something. Sometimes the speed perspective is a clearer way to say something. And let's all focus on testing and treatment and see what we can do about HIV. And thanks so much to everybody, and especially you, for your attention.